Imagine everything you think you know about how the universe is held together suddenly being tossed out of the window. For the last few decades, astronomers have been operating under one fundamental golden rule. Galaxies cannot exist without dark matter. It is the invisible scaffolding of the cosmos. It is the cosmic glue that provides the extra gravitational punch needed to keep stars from flying off into the void. We have been taught that a galaxy is essentially a giant clump of dark matter with a little bit of glowing gas and stars sprinkled on top like glitter. But a team of scientists just pointed their telescopes at a ghostly, thin patch of space and found the impossible. A galaxy named NGC 1052 DF2. That appears to have absolutely zero dark matter. It is like finding a bridge held up by nothing, or a skyscraper with no foundation. This discovery has sent a shockwave through the scientific community because paradoxically, finding a galaxy without dark matter might be the strongest evidence ever found that dark matter actually exists. Today, we are diving into the heart of a cosmic mystery that is rewriting the laws of physics and forcing us to question the very fabric of reality. To understand why this is such a massive deal, we first need to talk about why we needed dark matter in the first place. Back in the 1970s, an incredible astronomer named Vera Rubin was watching how galaxies rotate. According to the laws of physics laid down by Newton and Einstein, the stars at the very edge of a galaxy should be moving much slower than the stars in the center. Think of it like a merry-go-round. If you're standing right in the middle, you're just spinning in place. If you're hanging on to the very edge, you feel the pull much more intensely. In a galaxy, gravity is the force holding everything together. All the visible matter, the suns, the planets, the black holes, provides that gravity. But when Rubin looked at the edges of galaxies, she saw something that didn't make sense. The stars at the far reaches were orbiting just as fast as the stars in the middle. Mathematically, they should have been flung out into deep space. The only way they could stay attached was if there was a massive amount of invisible matter providing extra gravity. They called it dark matter because it doesn't emit, absorb, or reflect light. We can't see it, but we know it's there because we can see what it does to the things we can see. For nearly 50 years, this was the bedrock of cosmology. We estimated that dark matter makes up about 85% of the total matter in the universe. It was seen as an essential ingredient. You couldn't grow a galaxy without it. The theory was that in the early universe, dark matter clumped together first, creating gravitational wells that then sucked in the regular gas and dust to form stars. No dark matter, no galaxy. That was the law. Until astronomer Peter Van Dokkum and his team looked at a specific class of objects called ultra-diffuse galaxies. These are strange, ghostly things. They can be as large as our Milky Way, but they have about 100 times fewer stars. They are so thin you can literally see other galaxies right through them. When they studied the motion of star clusters within DF2, they did the math, checked it twice, and then checked it 100 more times because the result was terrifying. The stars were moving exactly as they should if there was only visible matter present. There was no missing mass. There was no invisible glue. It was a galaxy that was purely made of atoms, just like us. This shouldn't be possible according to our current models. If dark matter is the foundation of galaxy formation, finding a galaxy without it is like finding a house that was built in mid-air. The immediate reaction from many scientists was skepticism. They thought it had to be an error in distance measurement. If the galaxy was closer or further away than we thought, the math would change. But subsequent studies using the Hubble Space Telescope confirmed the distance. DF2 really is a standalone galaxy, and it really is missing its dark matter. But here is where the logic gets truly mind-bending. For years, a group of scientists has argued that dark matter isn't real at all. They believe that we don't need invisible particles to explain the universe. Instead, they think our understanding of gravity is wrong. This theory is called modified Newtonian dynamics, or MOND. They argue that on huge galactic scales, gravity simply behaves differently than it does on Earth. Now, if MEN were true, then every single galaxy in the universe should show these extra gravitational effects because it's a law of physics, not a substance. If gravity is just stronger at long distances, it should be stronger everywhere. But the existence of DF2 proves that isn't the case. If you have some galaxies with extra gravity and some without it, then that extra gravity cannot be a fundamental law of the universe. It must be caused by a substance. Something that can be present in one place and absent in another. By finding a galaxy that lacks dark matter, we have essentially proven that dark matter is a fezing that can be moved around, stripped away, or lost. It has moved from being a theoretical correction to a tangible, albeit invisible, part of our world. But how does a galaxy lose its dark matter? This is the technical mystery that scientists are currently racing to solve. One theory is that DF2 was formed in a high-speed collision between two larger galaxies. Imagine two massive clouds of gas and dark matter smashing into each other at millions of miles per hour. The dark matter particles, which don't interact with anything except through gravity, would just sail right through each other like ghosts. But the gas clouds, made of regular atoms, would slam into each other, heat up, and slow down. Over time, that stalled gas could collapse under its own weight to form a new, small galaxy located far away from the original dark matter halos. This would create a second-generation galaxy, made entirely of recycled star stuff, but lacking the dark matter foundation of its parents. If this is true, it means the universe is even more dynamic and violent than we suspected. Another possibility is that a nearby massive galaxy literally stole the dark matter. DF2 is part of a larger group of galaxies dominated by a massive elliptical galaxy called NGC 1052. Gravity is a greedy force. It's possible that as DF2 orbited this giant, the tidal forces reached out and stripped away the outer layers of the galaxy. Since dark matter usually sits in a wide halo around a galaxy, it would be the first thing to go. But this theory has holes. Usually, tidal stripping is a messy process. It leaves long tails of stars and gas behind like a crime scene. DF2, however, is remarkably symmetrical and smooth. It looks like it has been at peace for a very long time. This lack of visible trauma makes the stripping theory harder to prove, but in space, things are rarely as simple as they look. The technical implications for our computer models of the universe are staggering. We have spent decades building massive supercomputer simulations like the Illustris project. These simulations use millions of CPU hours to recreate the history of the universe. They almost always result in a universe filled with dark matter halos. If we can't explain how a galaxy like DF2 exists, it means our simulations are missing a key piece of physics. Perhaps dark matter can interact with itself in ways we haven't mapped yet. Perhaps there are dark forces that only affect the dark sector of the universe. Every time we find an anomaly like this, it's like a bug report for the universe's source code. We have to go back in, find the error, and update our understanding. Think about what this means for our search for the dark matter particle itself. For years, we have been building billion-dollar detectors deep underground, waiting for a WIMP, a weakly interacting massive particle, to bump into an atom of xenon and give off a tiny flash of light. We have been assuming that dark matter is everywhere, constant, and unchanging. But if some galaxies can lack it entirely, it tells us that dark matter is more fluid. It suggests that our local neighborhood in the Milky Way might be unusually dark matter heavy, or perhaps we are in a dry patch. This discovery helps us narrow down what dark matter could be. If it can be separated from regular matter, it confirms it must be a non-baryonic particle. It cannot be just dim stars, cold gas, or stray planets. It must be something fundamentally different from the stuff that makes up our bodies. Van Dokkum's team didn't stop with just one galaxy. They found a second one, DF4, that shows the same characteristics. Finding one could be a fluke. Finding two is a pattern. It suggests that there might be a whole population of these naked galaxies out there, hidden in the dark, waiting to be discovered. These ultra-diffuse galaxies are the new frontier of astronomy. Because they are so fragile and thin, they are perfect laboratories for testing the limits of gravity. In a big, heavy galaxy like ours, the dark matter and the regular matter are all tangled up together. It's hard to tell where one ends and the other begins. But in these ghost galaxies, the components are separated. It's like being able to study the heart of a machine by taking it apart piece by piece. Let's talk about the Dragonfly telephoto array, the instrument used for this discovery. It doesn't look like a traditional telescope. It looks like a bunch of high-end camera lenses strapped together on a mount, because that's exactly what it is. It was designed by Van Dokkum and his colleagues to solve a very specific problem. Large telescopes are great at seeing small, faint things far away, but they are actually pretty bad at seeing large, very faint, spread-out things. It's like trying to see a thin cloud through a microscope. You lose the context. The Dragonfly array is designed to detect ultra-low surface brightness. It can see the whispers of the universe that the big observatories miss. This is a great reminder that in science, you don't always need the biggest, most expensive tool. You need the right tool for the job. Innovation often comes from thinking about a problem from a completely different angle. What does this discovery do to the standard model of cosmology, known as lambda CDM? It puts it under a microscope. Lambda represents dark energy, and CDM stands for cold, dark matter. This model has been incredibly successful at explaining the large-scale structure of the universe, but it struggles with the small stuff. It predicts thousands of small satellite galaxies around the Milky Way that we just don't see. This is called the missing satellite problem. Now, with the discovery of galaxies without dark matter, the model has even more explaining to do. Some theorists are suggesting that we might need a warm dark matter or self-interacting dark matter to bridge the gap. We are in a period of what Thomas Kuhn called a paradigm shift. The old rules are failing, and the new ones haven't been fully written yet. This is the most exciting time to be interested in space. We are living through the golden age of discovery. For centuries, we only knew what we could see with our eyes. Then we built telescopes and saw the planets. Then we found that the stars are suns. Then we found that our galaxy is just one of billions. Now we are learning that the stuff we can see is just the foam on top of a deep, dark ocean of invisible matter. And just when we think we've figured out how the ocean works, we find a patch of water that doesn't have any foam. It forces us to ask, what is the foam? Why is it here and not there? Every answer leads to 10 more questions. Imagine the night sky from a planet inside NGC 1052 DF2. Because the galaxy has so few stars and no dark matter to concentrate them, the sky would be incredibly dark. You wouldn't see a glittering river of the Milky Way. You might only see a few dozen bright stars scattered across an endless black void. You would be living in a world that is pure, in a sense, made only of the atoms we understand. But it would be a lonely existence. Without the gravitational pull of dark matter, the galaxy wouldn't have been able to hold on to its gas as easily. Star formation would have slowed down and stopped billions of years ago. It would be a galaxy in slow motion, a place where time seems to stand still. The discovery also has massive implications for our understanding of the Big Bang itself. If galaxies can form without dark matter in certain conditions, was it always that way? Or is this a recent development in the history of the universe? We are looking back in time when we look at these galaxies. DF2 is about 65 million light-years away. That means we are seeing it as it was when the dinosaurs were disappearing on Earth. In the cosmic scale, that's actually quite recent. We need to find galaxies without dark matter that are even further away, billions of light-years away, to see if they existed in the early universe. If we find them, it would mean that the X-scaffolding theory of dark matter is partially wrong. It would mean that regular matter can occasionally go it alone and build its own structures from scratch. Technical enthusiasts should also keep an eye on the gravity debate. While the discovery of DF2 is a blow to the current versions of MOND, it doesn't mean those researchers are giving up. They are already working on new versions of the theory that can explain how certain environments might cancel out the modified gravity effects. Science is a constant back and forth. It's a battle of ideas, and the only judge is the data. At the moment, the dark matter as a substance camp has the upper hand, but in physics, the underdog can win at any moment with one single piece of evidence. We have to consider the dark buffer theory. Some scientists think that maybe the dark matter isn't gone, but it's just in a form we've never seen. What if dark matter can take on a liquid or superfluid state? In that state, it might not clump around stars the way we expect. It might flow through the galaxy and out the other side, leaving the stars to move on their own. This is highly speculative, of course, but when the data tells you that a galaxy is missing 85% of its mass, you have to start considering the impossible ideas. We are looking for a needle in a haystack, but we aren't even sure if the needle is made of metal or if the haystack is even a haystack. The search for more of these galaxies is now a top priority for the next generation of observatories. James Webb Space Telescope, with its incredible infrared sensitivity, will be able to look at the star clusters in these galaxies with unprecedented detail. It will be able to tell us exactly how old those stars are and what they are made of. This achemical fingerprinting will tell us the history of the gas that formed them. If the gas was pristine, it confirms the collision theory. If the gas is full of heavy metals, it means it was recycled from previous generations of stars. Each photon we collect is a piece of the puzzle. There is also the ghost in the machine problem. In our current simulations, when we try to create a galaxy without dark matter, they tend to be very unstable. They should fly apart or be crushed by the gravity of nearby large galaxies. The fact that DF2 is still here, looking calm and stable, is a slap in the face to our current understanding of structural stability in space. It is a zombie galaxy that shouldn't be standing. Yet it is. This suggests that regular matter is more resilient than we gave it credit for. It can maintain its structure even without the invisible support of dark matter. What does this discovery mean for you? It means that we are currently living through one of the most important chapters in the history of human knowledge. We are the first generations of humans to even know that dark matter exists, and we might be the ones to finally solve it. It's a reminder that the universe is far more complex and mysterious than we can imagine. It's an invitation to stay curious. The experts don't have it all figured out. There are still massive gaps in our knowledge, and that is a beautiful thing. It means there is still room for new ideas, for new geniuses, and for new ways of looking at the stars. The galaxy NGC 1052 DF2 is more than just a cluster of stars. It is a lighthouse. It is shining a light on the flaws in our theories and guiding us toward a deeper truth. It tells us that dark matter is not just a mathematical fix, but a real physical substance that has its own life, its own movements, and its own absences. It tells us that gravity is a nuanced and complex force that we are still just beginning to grasp. And most importantly, it tells us that whenever we think we have the universe figured out, it will always have a surprise waiting for us in the dark. So, as we look up at the night sky, we have to realize that what we see is only a tiny fraction of what is actually there. We are like people looking at the lights of a distant city at night. We can see the glowing windows and the street lamps, but we can't see the roads, the buildings, or the people. We are trying to map the city based only on the light, and now we've found a single street lamp that is floating all by itself in the middle of a dark forest. It doesn't belong to the city. It's a whole new kind of light. Our job now is to find out why it's there and what else is hiding in the forest. The discovery of a galaxy without dark matter doesn't just change our maps of space, it changes our perspective on how much we still have to learn. It's a humbling and thrilling moment. We are standing on the edge of a new understanding of the cosmos. The invisible scaffolding has been revealed by its absence. The laws of physics are being tested, and the universe, as always, is proving to be far more wonderful and strange than we ever dared to dream. The galaxy that shouldn't exist is very much real, and it is the key to unlocking the secrets of the dark. Keep looking up, stay curious, and remember that sometimes the most important thing in the universe is the thing that isn't there. That is the true power of discovery. It doesn't just show us what is, it shows us what could be. And in the vast, unexplained stretches of space, the possibilities are literally infinite. This is just the beginning of the next great era of space exploration, and you have a front row seat to the unfolding of the ultimate cosmic mystery. Stay tuned, because the universe is about to get a whole lot more interesting.